In this video, we're going to be taking a look at two different problems that combine momentum and energy. Now, when you're taking a look at a certain scenario, the key is to recognize when to apply energy concepts and when to apply momentum concepts. Now, both of them deal with the conservation of each of them, which means the total amount of momentum or energy before something happens is the same as the total amount of either of those after it happens. Now, what I would do is if I was looking at a scenario like this, like a ballistic pendulum where a bullet is striking a block and then both of them are rising together, I would generally say when there's some sort of collision, that's when you're going to apply the momentum concepts. And then with energy, oftentimes you will apply those when there are changes in height. Not all the time, but I would say generally speaking, those are fairly true. So in this case, we have a bullet coming in, colliding in the beginning, rising up with a certain amount of height. So in my mind, I'm going to use momentum and then energy. For the second one, I have a block that is up high, that slides down, that collides afterwards. So I'm going to go with energy and then momentum. So let's go ahead and check out these cases and see what we need to do moving forward. So let's go ahead and take a look at this first problem. I changed the mass to 0.05 kilograms. I noticed that I was a decimal place off. And we're starting with a collision. So I'm going to start off with some momentum ideas. So all the momentum before the collision equals the momentum after the collision. And with those ideas, I can go ahead and solve for the velocity of the entire system. All right, so that ended up being a pretty easy calculation. We have the momentum of the bullet, 0.05 times 200, which equals 10 kilogram meters per second, 0 for the block at rest, and that equals the mass of the entire system, 2.05 total, times the velocity. So just divide both sides by 2.05, and I have a velocity of 4.88 meters per second. So now I'm just focused on a single block with an increased mass of 2.05. I'm going to go ahead and apply my energy concepts. So at the bottom, we have a bunch of kinetic energy. And because that's my baseline height, we can basically call this a height of 0. And it's going to swing up to some unknown height that we're going to solve for. So we have a bunch of kinetic energy that is eventually going to get transformed all into potential energy once the system reaches its maximum height. Now, with that being said, let's go ahead and plug in all of our values that we have, our original values, and then also this VF as well to solve for that unknown height. All right, when I set my 1/2 mv squared equal to my mgh, my masses drop out. And then I just have 1/2 times the velocity squared divided both sides by the 9.8 in blue. That left me with a final height of 1.22 meters as our final answer. So let's go ahead and clear some space and go ahead and take a look at this second problem. Now for the second one, we are starting with some energy ideas because we just are focusing on our 2 kilogram block, and then it's eventually going to collide with the 3 kilogram block over here. And that's when we're going to implement some of our momentum and collision ideas. So first of all, the block is at rest at the top of a ramp, so it has a bunch of potential energy up top. And then when it slides to the bottom, that all changes to kinetic energy. Now, we don't have this height quite yet, but we do know it slides down 2 meters. So I'm going to go ahead and use the sine of 30 degrees, which equals the opposite over the hypotenuse. So I'm going to multiply both sides by 2, and that's going to leave me with a height of 1 meter. All right, so now we're ready for our calculations. Let's go ahead and set that potential energy equal to that kinetic and see what we get for the final velocity of our red 2 kilogram block at the bottom of the ramp. All right, so we set our mgh equal to our 1/2 mv squared once again, and the masses drop out as usual. And then I multiplied both sides by 2 to get rid of that 1/2. So it's basically 9.8 times 1, which is still 9.8. So times 2, which gives us 19.6 equals v squared. So I square root of both sides to find a final velocity of 4.43 meters per second. So now we can go ahead and start the collision portion of our problem. Now that we know the velocity of the 2 kilogram block is 4.43 meters per second at the bottom of the ramp. So assuming this is a perfectly inelastic equation, just like the previous one, we're going to have the 2 kilogram block sticking to the 3 and then figure out what happens to the final velocity of both of those together. So let's go ahead and set up the momenta before the collision, after the collision, and then see what we get for our final velocity. So when we took the momentum before the collision, we have the m times v found from the previous part of the problem that we pull over. So we know the momentum of the 2 kilogram block at the bottom of the ramp. The 3 kilogram block is at rest, so it has a momentum of 0 kilogram meters per second. So all we had to do is combine the two masses and make them one big 5 kilogram system, divide both sides by 5, and then we have a final velocity of 1.77 meters per second. So to sum things up, obviously you want a good foundation of understanding conservation of energy and conservation of momentum first before you get into these types of problems. And as I said, generally speaking, not for all problems, once you see the collision part, that's where you're going to want to apply the momentum concepts. And then when you see changes in energy, oftentimes resulting in changes in height, then you're going to want to implement a lot of those energy ideas. But I hope that was helpful in helping you see those two examples along with the explanations. Thank you for watching and listening.